all yours.
Welcome to the 73rd OWARS seminar. My name is Jennifer Alonso Garcia, and I will be chairing today's seminar together with my colleague, Silvana Pacenti. The speaker today is Karim Barigou. This seminar will be recorded and made available on the OWARS website for a week. So just, of course, for those who are always here, you know, you're muted during the seminar, but you're welcome to pose your questions in the Zoom chat. Silvana will be monitoring the questions and put them to the speaker. And at the end of the talk, you will also have the opportunity to unmute yourself and ask the questions directly. Now to today's speaker. Karim is Professor of Actuarial Sciences at the Louvain School of Management and the Institute for Multidisciplinary Analysis and Quantitative Modeling, IDAM, at the University Catholique de Louvain in Belgium. His research interests are in life insurance and its interplay with quantitative finance. Today's presentation is titled Bayesian Mortality Modeling with Pandemics, a Vanishing Jump Approach. And this is joint work with Julius and Leucht. Karim, the screen is yours.
Thank you very much, Jennifer, for the kind introduction. So first of all, thank you for the invitation and thank you all for joining this seminar. So today I would like to discuss about mortality modeling and especially how you can adapt mortality modeling to take into account pandemics. And as the title indicates, it's a Bayesian approach. I will motivate the reason for that. And one of the key points of the approach is to take into account the vanishing effect of the pandemic, something which was not done before in the literature. So I will start from a broad introduction and start from the very basics, so which is the Leucht model, and then we will go step by step to our modeling approach. So first of all, it's about how to adapt mortality modeling for pandemics. The standard approach in mortality modeling is the Leucht model, but definitely such a model is in fact inadequate to capture pandemics for different reasons. One of the key reasons is that in this approach, the mortality is driven by a random walk with drift. And by nature, I mean, a random walk is a normal noise. So it does not account for large unexpected jumps, as we can see for pandemics or world wars. In fact, in the paper of the Lee and Carter, they had one extreme event, which was the 1918 influenza, the Spanish flu. But what they did, in fact, was kind of simple. They look at this as with an intervention model, and in fact, they just remove the influence. Of course, this has important consequences in insurance. I mean, you cannot just remove these extreme events because when you do that, in fact, you are narrowing your confidence intervals. And in insurance company, in insurance, you have to compute, of course, solvency capital requirements for mortality risk. And in that case, if you just remove this extreme event, you will in fact underestimate your SCR, your solvency capital requirements. So that's very important to take into account these extreme events, and that's the purpose of this presentation. Of course, we are not the first to look at pandemic effects in mortality dynamics. There are quite a lot of literature on that. I would say the first approach is, I would say, the outlier detection, as I've just mentioned. Some people will just detect some outlier and sometimes even completely remove it, consider this as just non-repetitive. They will not happen anymore in the future. Another type of literature is the jump processes. So we'll focus on that today. There are essentially two directions, either permanent jumps. So as the name indicates, it assumes that the pandemic will have an effect, let's say, forever. It will affect all the future mortality rates. And another approach is the other extreme, which is a transitory one-period jumps. So it will only affect the mortality the year after. So we'll look at that afterwards. Another stream of literature is the extreme value theory. The approach is, in fact, relatively simple. The idea is, in fact, to replace the random walk with drift with, for instance, Pareto distribution to take into account these extreme events. Also, following COVID-19, there have been different papers about how to adapt mortality modeling for pandemics. So I mentioned here some papers, but in fact, in all these papers, when they consider vanishing effect, this vanishing effect is either simulated or based on expert judgment. And the purpose of this presentation is not based on expert judgment, but we would like to estimate this vanishing effect based on, real data, and to quantify also the uncertainty around such vanishing effect. In fact, more broadly, we'll not only consider single population, but we will also propose some multi-population model, and we'll show using COVID-19 and OWARS data in and out of sample performance. So just to give you an idea, but I think you are kind of familiar with the mortality dynamics. So here, just for illustration, is the dynamics of log death rates in the case of Spain. So of course, in the last 40 years, we have seen mortality improvement, but typically in 2020, we had a peak, and now this peak is vanishing. Of course, there is still the uncertainty whether we'll go back to the normal trend or if the new trend will be different. So, well, in our case, we will not make a new trend afterwards, but the idea is to capture this vanishing effect. So I will start from the basic Leucht model, and then I will discuss some different extensions. So the main component of a mortality model is, of course, the death rates. So we denote by dxt the death at age x and time t, and ext the central exposure at age x and time t. And our focus is therefore the central mortality rate denoted by mxt. So the Leucht is given by the following dynamic. I guess you are most of you are already familiar. So you have a first component alpha x for the age specific effect. Then the kappa t captures the mortality improvement, and the beta x will essentially capture which age has benefited the most from the longevity improvement. Just as an illustration, just to have the model in mind. So here, for instance, is the calibration for Belgian data. So you see that you have the kappa t decreasing with a peak in 2020. You have the alpha x increasing by age, and then the beta x, which captures which age has benefited the most. So in this case, we see that between 70 and 80, that was essentially the age that benefited the most from the longevity mortality improvement. So in the Leucht, they assume that the period effect is following a random walk with drift. So it means that the CT here, the random noise, is normally distributed. So a few papers have proposed extensions for pandemics. A first extension was the paper of Cox et al. So as you can see, basically you have a component YT and T for the jump, where you have first the jump intensity NT, which is Bernoulli with probability P of occurrence, and then you have the severity given by a process YT. Of course, the first issue of such a model is, as you can see, once there is a jump, it will affect all the future kappa t. So it means that if you have a jump in 2020, the severity, it will be in a pandemic state for all future years, which is kind of a pessimistic approach. Another approach proposed by Chen and Cox, in fact, this is the same Cox from the two papers, it's the following, where you see that you have a component at time t, and then you have which is compensated by an effect at time t minus 1. So it means that in that case, if there is a pandemic, then it will just cancel the year after. So in fact, in that case, you just have the next kappa t which is affected. So we see that with these two approaches, we are in like two extreme situations. In one hand, all the future kappa t are affected. On the other hand, only one kappa t is affected. So we would like to have a kind of in-between situation where there is future years that are impacted, but then it vanishes. So there are two problems of such approach. First, as I mentioned, there is no vanishing effect over a few years, as we can see in the case of COVID-19. Second point, which is also quite important, is that here the impact is on the capacity. The problem with that is that it assumes, in fact, that the age pattern of the pandemic is the same as the one of the general mortality improvement. What I mean by that is that if you, if you work on the capacity, you will see here, if you go back to the Leucht, you will have the same beta X in case of pandemic or in case of longevity improvement. But in general, we can see that the longevity improvement usually it's for young ages, while the pandemic often it will affect the older people. So in fact, we would like to disentangle the effect of the age-specific effect in case of pandemic and of the normal trend. So there is no other possibility that to work on the log death rates instead of the capacity, and that was one proposition by UNE in 2015. It was to propose then a pandemic effect on the log death rates. So in that case, you have a beta X J that will capture the age-specific effect from the pandemic, and then you have the jump process JT, which, as before, as a component of jump intensity multiplied by jump severity, which is Gaussian. So here we see that the nice thing of such a model is that you have age-specific effect for the pandemic. The only issue is, of course, that you have, again, mortality jumps that are just one-year events, and there is no vanishing effect from such a model. So we would like to start from the Liu and Li and then propose different types of adaptations that would probably better represent the pandemics. So we have considered first two quite simple, I would say, the two natural extension to take into account the vanishing effect. So we started from the Liu and Li, but then here in that case we have considered two types of structure for the JT. The first one is an autoregressive structure, where you see you have a parameter A that will controls the rate of decay. And then you have a moving average here with, again, a parameter B to capture the effect, the vanishing effect. So what's the main difference between the two approaches? As you can see, first, in the autoregressive structure, you see that once there is a jump at time t, it will affect all the future years after with a decay of A. So you have A squared, and so on. While in the moving average, you still have an impact on the year after, but afterwards, there is no more impact 2 or 4 years after, 2 or 3 years after. So we see that there are these two situations. So there is the autoregressive where it's more long-term, let's say, and the moving average, which is essentially you have a pandemic over 2 years. And then, of course, it's an extension of the Liu and Li because you recover the Liu and Li in case A or B equals 0. So how do you estimate such a model? There are different approaches. I would say the common approach is either to work on the mortality rates directly or the mortality improvements. In fact, we decided to work on mortality improvements. There are several reasons for that. But in fact, if you work on mortality improvements, so the first difference of death rates, in fact, you have less parameter to estimate, and in fact, you have less identifiability constraints. So in this paper, I mean, we looked at the mortality improvements, ZXT, and we worked directly on the ZXT. So most of the mortality models suffer from identifiability issues, meaning that you have several parameters that optimize the likelihood. So here in that case, you can see that you can write ZXT as a product of two matrices, And you see that if you multiply by a matrix A, two times 2, you see that you can multiply Bx and kappa t by the inverse, and in fact you will have you will recover the same parameters. So we see that there are 4 free parameters, so we need 4 constraints at least to identify the ZXT. So we use kind of standard identifier constraints on the beta and corner constraint on the on J and K. One important point is that if you have these identifier constraints, in fact, you can perfectly identify the ZXT. But what is important is that even though you can identify the mortality improvements, you need additional constraints if you want to identify the jump occurrences NT. So it's not straightforward to identify such a model, which is quite intuitive, I would say, because even though you have a jump process that you can observe, trying to identify which year the process started jumping, let's say, it's not so straightforward because there is this vanishing effect. So it can be that there is 1 jump, 2 jumps, and so on. So I would say it's not straightforward, but in the paper we were able to derive some sufficient conditions to make the model identifiable. And then for the estimation, we worked in a Bayesian framework. There are several reasons for that, but I would say the main reason for that is when you work in a Bayesian framework, you have a full distribution for all your parameters. So you don't, if you work in a frequency setting, usually you have to do some bootstrap, but here you have the full distribution for all the parameters directly. For the validation, we consider in and out of sample performance, but in the case of the COVID-19, of course, usually it's better to have out of sample performance if you want to forecast, look at the forecasting performance. But given that the pandemic just happened, we couldn't do some out of sample performance in that case. So we consider in sample performance using WIC and LuCV, and then we compare with the Liu and Li model. Of course, because we work in a Bayesian framework, we need to specify the prior. So I will not go too much into the detail, but I wanted at least to mention about the prior for the P, so the jump priority. So we put a prior of beta 120. So if you are not familiar with the beta, in fact, we put a lot of mass around 0. And there's an important reason for that. I mean, if you have a prior P on the jump priority between 0 and 1, just a uniform, usually the model will not converge because it cannot distinguish between, I would say, the normal trend and the pandemic event. So if you really want the model you want to tell the model that P is some extreme events, you have to tell him that P is relatively low. So that's important information to put in the prior if you want the model to converge. Otherwise, the other parameters are quite uninformative and general. So for our analysis, we looked at 3 countries, Poland, Spain, and the US. We looked over a bit more than 30 years. One can consider that 30 years is maybe not enough for pandemic events. We can discuss that afterwards. But one reason for that is that before 1990, for some countries, there were a change of trend. And the issue with that is if you look at the Lee Carter over the long term, I mean, you need to make also breaks over the trend if you want to take that into account. What I mean by that is that there is always, on the one hand, you would like to have more data, but the more data you have, the more breaks you can have in your trend for the kappa t. So in that case, we just wanted to look at 1990 and afterwards, because that's essentially the moment where we see a clear trend from that year. So the first result that we that we obtained. So for the three countries, so US, Spain, and Poland, we compared first the Liu and Li, and the AR is for the autoregressive extension, and MA is for the moving average extension. What is interesting is that for the three countries, the moving average was doing the best in terms of WIC and LUCV. So basically what it means that essentially it seems that the pandemic had an effect intuitively over 2 years. So during the pandemic and the year after, but it doesn't seem that it has a very long autoregressive effect over several years. At least it seems that the MA1 is performing the best for the three countries. Then I will discuss a little bit about the different parameters and results. What is good with such a Bayesian approach is we can have a look at the posterior estimates. So here, for instance, we look at the posterior estimates of the jump process NT for all the three countries, and we see that definitely it detected with priority with a certainty with priority 1 a jump in 2020 and 2021 for Poland and the US, only one in case of Spain, and no other jump. So it is quite aligned with what we could have expected. Then here we can have a look at the posterior distribution for the severity. So here, why is the severity of the pandemics? So we can see what was the severity in 2020 and 2021 with a higher severity for the US, but then decreasing in 2021. And then we have also the estimates with a credible interval for the mean and the standard deviation of the severity, so the process Y, where the three countries seems to be aligned in terms of uncertainty. And then, so here we also obtain what's the jump priority for the three processes. So we see that on average, the jump priority is 5%. Can be considered quite high, but also we have to take into account that we had 30 years of data. So of course, with only 30 years, the priority of a jump can be quite high, of course, over this interval. And then we also had results over the vanishing parameter. But I will not discuss too much about that, but it gives at least indication where we are situated and also the uncertainty. So we see that here the vanishing parameter was the highest for the US. So here it was the case of the autoregressive, and we had also vanishing parameter for the moving average. Also, another point that I wanted to discuss is about the idea of whether we had a power shift of the mortality curve. So during the COVID-19, there was a lot of research arguing that there was a power shift of the log mortality curve. So here I've just illustrated two illustrations from two different papers. On the left, it was a graph from Milewski, where there was in fact, he was arguing that we had a pre-virus situation, and then there was a power shift of the term structure of mortality during the virus. And on the right, it was more about the death in England and Wales, if I remember well, from Cairns et al., where we could also see a parallel shift of the a parallel shift on for deaths. So, of course, a natural question is whether our model is aligned with such approach. What is nice, in fact, with our model is that we can easily have a look at what's the impact, the age-specific impact of the pandemics. Because if you look at the dynamic here of the log death rates, we can see that there is, in fact, we can decomposed in two parts. There is the first part which is related to the Ricarter, and then there is the second component here on the right, beta XJT, which is in fact related to the pandemics. So if we want to have a look at the impact across ages, one possibility is to say, well, the death rates is in fact the death rates in the normal situation, which is captured essentially by the Lee Carter, multiplied by a constant C, which will essentially capture the increase due to the pandemic situation. So that's what we obtained. So here is essentially the age pattern of the beta xj. So here we can see what's the different age pattern due to the pandemic. So here, for instance, in the case of the US, and it was also consistent with other literature, it was essentially the middle age class, which was mostly affected by the COVID between 20 and 50. In the case of Spain, there was like kind of bimodal situation with a peak of the old age people around 80, but also kind of there was another peak around 30. And then in the case of Poland, it was more like the other situation where we had more deaths for old people. So as you can see, the three are clearly not parallel. In the case of the US, it's more the youngest middle age class, middle age, while for Poland, it's more the old age people. So we can see that there is a kind of heterogeneity. So I would say that if one used the power shift assumption, one needs to be careful, because we can see for different countries we have sometimes completely different age patterns. So one needs to be careful about it. Another point also about the COVID-19 is we can have also confidence intervals for the increase of death rates during a pandemic. So what do we want to capture here is to say, well, we have our, let's say, standard death rates, and we would like to know what's the percentage increase by age class in case of a pandemic. We would like to capture that, but also to capture the uncertainty around that. So here for the three countries and by age class, what you can see is, so the dotted dark line is in fact the COVID increase in 2020 compared to the 4 years before. And the different shades are in fact the confidence intervals of the percentage increase based on our model. So here what we can see is clearly what's the uncertainty by age class and where we are situated. So as you can see, usually the COVID increase was around the 90-95% interval, 99% quintile. So don't worry, the one that we see on the top is already the 99. So normally we should not see that happened, but we see that at least what is good with such a model is that we are able to capture what's the percentage increase by each class and what's the uncertainty for the uncertainty around such increase. Then we also did some forecast, and we wanted, in fact, to compare the forecast of a standard Lee Carter model with our proposition. So here you see a forecast of, first, the Lee Carter is the one in kind of blue, and the other colors are the confidence interval of our own model. So as you can see, that's if we look at the 90% frequency model and the 90%, we see that in our case we have slightly higher confidence in credible intervals, and especially on the top, which means that we are kind of more conservative on the mortality risk, which is kind of natural. I mean, here the difference is due to two effects. First, in fact, we compare the frequentist approach. So in our paper, we have a Bayesian approach, so we account for parameter uncertainty. So that's one point. And second point, our model accounts for pandemic jumps. So we should also expect to have more uncertainty on the top side, I mean, on the increase of the potential increase of mortality risk. Of course, actuaries use such a graph to compute solvency capital requirements. So from this graph, it seems that if one wants to compute the SCR, the solvency capital requirement for mortality risk, our model would suggest to increase the solvency capital requirement for mortality risk, which kind of makes sense, right? Taking into account the pandemic effects. Then afterwards, we have consider, so we consider pandemics, but also world wars. And because in fact, during the world wars, we also have extreme events. We have a jump that lasts for a few years and then vanishes. And in that case, given that we have world wars, we can look this time not at in-sample, but out-of-sample performance. So we did two exercises. The first scenario was to train the model during World War I and then predict the mortality rates during the Second World War. And a second scenario that we considered was to train the model on both world wars and then predict afterwards, after the Second World War, to see if we are able, in fact, to better predict mortality rates during normal times as well. So we'll see what was the results. So we had these two situations. First, we trained the model during the during until 1943. So we stopped around the Second World War and then forecast over 5 years, because we also wanted to capture in the result the vanishing effect. And then in the second case, we trained the model over 80 years and then project over 30 years. So after the two world wars, to see if we are also able to predict in normal times. So we looked at 4 measures: log score, continuous ranked probability score, MSC, and MAA. And then these are the results. So we see our two proposition with autoregressive moving average compared to the Lee and Lee. And we see, depending on the score that we use, that AR or MA are doing a better job than the Lee and Lee. And if we look at the second case, well, in the second case, we do much better than the Lee Carter model. We can also see that in terms of forecast. So here, how you should read that one. You have the Lee Carter, which is the blue. So we see that the Lee Carter, so basically here it was calibrated with the 2 Second World Wars included, and then we forecast. So of course the Lee Carter, because the extreme events are captured in the volatility of the random walk, usually the Lee Carter will have very high confidence intervals, where in our case, because we have these extreme events captured within the model, usually we can sometimes expect, as we can see here, lower confidence intervals. So that could be a good argument for our approach. The second point is also about why our model is doing better. Is you can have a look at the dotted lines. So the dotted lines is the observed mortality, and then you can see the red line. So the red line is the mean autoregressive model that we propose. And the black line is the best estimate from the Lee Carter. So here we clearly see that our proposition is more aligned with the observed mortality. And what's the reason behind? The reason is very simple. In fact, when you have a jump and you just apply Lee Carter, of course, the jump will affect the volatility. So as you can see, you have a much more volatility because of the pandemics. But secondly, it will also affect your drift, so the mu from the random walk with drift. So because you have a jump, in fact, the jump will be in the mu. So basically, we see that here you have a best estimate of the Leucht, which is higher than our proposition because, in fact, part of the OWARS is in fact moving the drift to the top, right? So that's why we see that our proposition, so the mean autoregressive model, is doing a better job. So essentially, the main idea is that, in fact, the Leucht, you put everything together, where in our model, we are able to disentangle the normal trend and the pandemic effect. And usually, you will see that you have a better performance both for the best estimate and also for the uncertainty round. Because here, what we can see is that really, I mean, over 30 years, I mean, the mean is closer from our model to what was observed, but we can also see over 30 years, all the observed mortality was exactly in the confidence intervals. So, I mean, it was I would say, the perfect match because we have uncertainty, but just not too much, not just a little, but just the perfect uncertainty over 30 years. Or in the case of the Leucht, it would have been much too high, right? Then afterwards, we consider a multi-population extension. Of course, in the case of a pandemic, a multi-population is quite important because, as you can imagine, once you have a pandemic in one country, it will affect also the other countries. And therefore, it would make sense to have a shared pandemic, jump effect. So here what we propose is, again, the same kind of structure as before, but now we have an index C for the country. So all the parameters are indexed by C. So it's like we have the single population model. But now for the jump process, you see that you have an NT which is common for all the countries. So we assume that once there is a jump, a pandemic in one country, it will affect all the other countries. But they still have their own severity and their own age-specific effect because, as we have seen, the severity can be different from one country to another. But usually when there is a pandemic in one country, it affects the others. So then afterwards, we compare the single population, which in fact assume kind of independence between the countries, and the multi-population. And in fact, we found that with WIC and LUCV and both the autoregressive and moving average, that the multi-population was always doing better than the single population. So there is a clear advantage to have a shared common effect, jump effect for the different countries together. So here it's just an illustration. If we consider different paths for so you have the multi-population on the left, single population on the right. As you can see on the left, when there is a shock, it's at the same time for the three countries. Of course, the severity can be different from one country to another. Of course, that's what we would expect. But you see that there is the jump at the same time for the different countries. Where on the right, if you look at just independent single population, you can have very different scenarios and sometimes inconsistent scenarios between the different countries. So I believe it's important because multi-population that can be used for different countries, but also different regions in a single country. So that's important aspect to keep in mind. Another point that I wanted to discuss, so it's not in the paper, but in a previous version of the paper, we looked at the situation of Italy. In fact, the situation of Italy was quite interesting because here I showed the jump occurrence in the case of Italy. And as you can see, there is not only a jump in 2020, 2021, but there was also a jump in 2003 and so on. And then when we looked closer at the data, we found that it was due to heat waves. So in fact, yeah, I mean, the dynamic we had on the one hand heat waves, but which was, so here on the right you can see the graph where you see the peaks due to heat waves. Especially in 2003, there was an important heat wave in Italy. So of course, the natural question is whether our model is able to capture both pandemic and climate shocks. Usually, well, one possibility would be to say, well, in fact, the one difference between the two is that usually a pandemic lasts over potentially several years, while a heat wave is quite short in terms of, so there is a lower vanishing effect. So a simple solution would be to just split the vanishing effect due to pandemic on the one hand and the effect from heat waves. So in that case, you would observe something like this. So you would have a pandemic effect maybe around 0.3, 0.4. So this is the vanishing effect, so A2 due to the pandemic. And then on the left, you would have a another effect due to heat waves. That's one possibility, but in general, I would say that pandemic and climate shocks, in fact, quite different for different reasons that I've mentioned here. First is about the time frame. So usually pandemics, you can use, I would say, yearly data to detect pandemics, while for heat waves, usually you have to work with daily and weekly data. So if you want a model for pandemic and climate shocks, you don't have other choice than looking at more granular data. The second point is about the seasonality, where the pandemic over 1 year, well, of course, there is no seasonality if you look year after year, but if you look at daily or weekly data, you have seasonality, and then in that case, you would have to consider maybe a SARIMA process instead of a random walk with drift. And third point, which is often not considered in the literature, is the increased frequency and severity due to climate change. Because, for instance, even in our paper, we just assume a jump severity P, which is constant, but we can probably we can expect maybe, I don't know, for the pandemics, maybe we'll have for some reasons, maybe we'll have more and more pandemics in the future, more and more heat waves. So it's important that such jump process has a P, which is not constant, but time dynamic. And this can be quite challenging because then you have to work with maybe self-exciting processes and other types of process where the jump is itself dynamic. So this is also important point for future research. Okay, so I would like to conclude with different points. So first, we wanted, in fact, to show some single and multi-population models to capture the vanishing effect. So I hope that I convinced you that our model is doing a kind of great job to capture the vanishing effect. We were able to show it in sample with the COVID data, out of sample during World War I and World War II. And then we compare with the Leucht and Leucht model, both with the autoregressive and moving average. And basically we found some better performance overall. The good thing with the Bayesian approach is that you are able to capture the parameter uncertainty of all parameters, but including the vanishing parameter. There are still open questions for future research. The one that I've just mentioned is how we can take into account pandemic and climate shocks in a single approach. I think it's not obvious because, I mean, these are driven by different factors. The second point is about the jump occurrence, which might affect the mortality trend. So in our approach, we have a vanishing effect, but then we come back to the normal trend. But some people argue that due to COVID-19, we have maybe a new trend. Maybe the mortality improvement will not be as before. So that can be one extension of the model. And the third point is the advantage of the Bayesian approach is that we can include expert opinions as a prior distribution. So in our case, we didn't use expert opinions, but that's something that we can also include in our model. So yeah, I think thank you for your attention.
No, okay. Thank you very much, Karim, for this interesting talk. So for the audience, you can now unmute yourself, or you can raise your hand if you have questions, if you want to ask them directly, or you can also put them in the chat if you prefer. So maybe I don't see any raised hands as yet. Maybe I can ask a question that I was being curious about. It's more a philosophical question in that. So you model jumps, right? So you say, okay, you have the log mortality and then it jumps. Why a jump? Why not something that's very smooth but very spiky?
So what do you have exactly in mind? Like
No, I'm just wondering why there should be a jump, or is there a reason that there should be an actual jump, or should it be smooth?
Well, I would say when you start, there should be usually the pandemics just not. I mean, in my opinion, I mean the pandemic does not happen smoothly. So when you start, there is a jump, something quite sudden, but then once the pandemic is there, it's not like jumping in the other direction. I mean, it's smoothly vanishing towards no more. I would say no more trend, but maybe no more situation. I would say that usually when you have a pandemic, it happens quite suddenly, so in a span of maybe a few weeks. But then once the pandemic is there, it's, I mean, vanishing relatively slowly. So it kind of makes sense to say, well, we have a jump and then this jump vanishes. I mean, it would not make sense to say, well, a pandemic uh, arrives smoothly or increasing smoothly. Usually it's like it's sudden and then afterwards it vanishes. So I think it's quite representative of what you have seen with the COVID-19. And yeah, I believe that the jump I mean, is a nice modeling approach because there have been other approach, maybe with regime switching, things like that. But the problem with the regime switching is that you re-switch in one direction and then you re-switch in the other direction, which according to me does not really make sense, right? I mean, you are here and then you will say, okay, you have a jump of 20% for 1-2 years, and then you have a probability of jumping 20% down or something. But I mean, in reality, is not how it works, right? I mean, you have a smooth transition between the states, and well, I believe that's our model that is able to capture that.
Right, yeah, very interesting. Yeah, I guess it depends also on the time frame that you're looking at. If you look at like weekly data or daily data, then I guess if you go small enough, you can argue that it's a smooth and not a jump, right? But yeah, I see that. Are there any questions from the audience?
I have one.
Sure, go ahead.
So I'm thinking, so what you presented is a relatively sophisticated, it's very easy to understand, and the intuition behind it, it's more sophisticated than the classical Lee Carter. So then if you would be thinking of telling someone in the industry who might only use Lee Carter as a already sophisticated model, how to, as a proxy, try to mimic your effect, but in a more pragmatic model, what would be your recommendation? Or is it just like you need to go directly to the Bayesian world and apply these things?
Okay, thank you for the next question. Well, the Bayesian is not necessary. I mean, you can do our model in a frequency setting. I think it would already simplify the framework. But then you have to work then with well, maybe you'll have to do some bootstrap or other things to keep the uncertainty. But I think there is no real simplification that is possible. I mean, if you have a Leucht, I mean, there was some simple approach using weighting scheme, stuff like that, saying that, okay, you have this COVID data points and you put a certain weights. But I mean, usually it does not work, because when you do that, first, you are not putting the pandemic within your modeling approach. So, I mean, that's also an issue if you want to forecast future pandemics. And also, if you put some weights, in fact, you are reducing the uncertainty. So, I mean, if you have these points, you should not remove these points or remove the influence of these points. So, yeah, I mean, according to me, you should go for the for the full model. I mean, really to take into
No,
account
but
the
I was just
jump
thinking if there
and the
could be
vanishing.
something, you know, a little bit more pragmatic, because of course this is of great importance to have a proper mortality model for life insurance, pensions, etc. But then yeah, it just
Yeah, I mean,
and also I was wondering, in your future directions, you were talking about the jump occurrence might affect the mortality trend, and that makes sense. But then I was thinking, do you already see some changes? Because it's been, I mean, COVID has been already been a few years. So do you already see some indications that that might be the case, that the drift of kappa T, which classically is calibrated from the 70s, is already changing drastically?
well, from what I read and seen in the literature, it seems that there is a slowdown in some countries. So it might be that after the COVID-19, it will not be back to the normal trends, but the trend might be worse than what was before.
Right.
Of course, in our case, that's difficult to estimate, right? Because I mean, you work on yearly data, we just have a few data points, so it would be hard to estimate a trend just after the COVID, right? So, I mean, I think to properly answer this, we'll need a few time, I mean, more data, or at least a few years. Another possibility would be to look maybe at more granular data. Maybe if you look at monthly or weekly data, maybe you can better capture the new trend, let's say. But yeah, it seems that it affects a little bit the drift of kappa T. Yeah.
Okay. Thank you.
Are there any other questions in the audience? No, doesn't seem to be. Give another 1 or 2 minutes. Yeah. Well, if anyone if a question comes up, they can always reach out to Karim via email. So thank you very much again, Karim, for this very interesting talk. And hopefully it can be applied and people in industry will actually use a more sophisticated model. That would be great. Then let's thank Karim again, and I hope to see you all again in the next OWARS seminar series. Thank you.
Yeah. Thank you very much for the invitation. That was a great pleasure. And yeah, see you soon at the next OWARS.
Yeah, thank you.
Yeah, thank you. See you next time.
Bye.
Yeah, thank you. Bye.